Okay, let's derive the equations that govern the torque required to lift a load with a power screw. And so I've got here a clamp. It's not used typically to lift a load, but it does apply a force, so the principles are kind of the same. So as I screw the clamp clockwise, it forces this upwards, and if I had something up here on top of it, it would apply a force upwards on it, could lift it against gravity, or if I put something in here, it can of course clamp it. So let's figure out how much torque is required in order to screw this upwards and apply a given force. So if we know what force we're applying up here, equivalently what torque is required to push up against it. All right, so let's actually go ahead and draw this. I'm just going to draw this portion of the clamp, this the female thread portion. That's all I'm going to represent. That's this part here. I'm just going to assume that this is fixed, and there's a screw going through it. That's what I have here. And I'm going to apply the torque on the bottom end. Here's my handle. And here's the top of it. So it kind of doesn't really matter, but all right, I'll draw the foot up top, or the... Okay, and so we've got some sort of weight. Well, let's just show some sort of load that's acting on top here and that's pushing down on it. And this thread here, let's get a close-up of that. It's actually an Acme thread, but for the sake of analysis right now, let's just pretend it's a square thread. And so this is what it looks like up close. I'm going to draw the other side of that. Now it's got some sort of helix, so the teeth, if you look at the two sides, they're going to appear a little bit offset from one another. All right, so it doesn't really matter what happens up here or down here. Let's just look kind of, we've got these sloping teeth here. Here's the bottom of a tooth, here's the top of the next tooth. That's kind of what it looks like from the side. Exaggerated a bit. Let's investigate this tooth more carefully here. Right. You can kind of imagine the helix, it goes up. If I'm following this around the diameter, it goes up by a constant amount for a given angle that you sweep around. And so it turns out that if you unravel this helix, if I start up top here and I were to unravel that and make it be flat in a plane, what this looks like, if you don't wind it around a circle, like it is here, the bottom surface here, well, the bottom surface looks just like an angle, or a straight line if you unwind it. So the helix of the bottom there is kind of just a straight line if you unwrap it from the circle. And relative to the horizontal, it has a constant angle. And we're going to call that lambda. That's the lead angle. And we call it the lead angle because this distance here, well, we have we unwrapped a full turn, right? So this full turn, the length of that is pi times the diameter that we unwrapped it about. So if we look at the outer edge here, you know, and so if the main diameter, the major diameter is d, then this would be pi times d. It turns out that we're going to be interested in what we're going to call a mean diameter. So instead of looking at the very outermost diameter here, which would be here, we're going to look at, I'm going to blow this up even more a little bit. So here's a single tooth. We're not going to look at the outer, so let's do the other side as well. We're not going to look at the outer diameter, this d, nor are we going to, here, that's a very bad tooth there. We're not going to look at the minor diameter either, the inside of the tooth. That's the root diameter. We're going to look at something in the middle. We're going to look at this diameter. It's halfway in between. I'm going to call it dm, the mean diameter. dm is the average of d plus dr over 2. So drawn on this diagram, we're going to look at this diameter from kind of the center of the tooth to the center of the tooth over here. What's that diameter? We're kind of walking around the helix in the middle of this path that we have, because we've got a little surface, a little ledge that we're walking around upside down, I guess. And it's in the middle of the root diameter and the major diameter. So this is pi times dm. That's what the length of this thing that we just unwrapped is. And it's going to go up by an amount that is equal to, over that path, it's going to go up by amount L, which is the lead of the screw. It's equal to the pitch when we have a single start screw like this. All right? Let's see. And there's material up here. It doesn't really matter. We can draw it as a triangle, or as, you know, it's actually kind of quadrilateral sort of thing if we unwrap it. But it's usually just drawn as kind of a triangle for the sake of drawing a free body diagram. That's what we're going to end up doing here. Note also that this angle, I mean, maybe some basic geometry, this is going to be lambda as well. But I don't think that, yeah, that could come in handy. All right, so I'm going to just write up the relationship here that the tangent of lambda, and this will come in handy later, is L over pi dm, the rise over the run, L over pi dm, sine over cosine for that angle. So that's what the tangent of lambda is. Just keep that in mind. All right, so think about that tooth, or that male tooth, and it's kind of, well, let's bring this out again. If I'm pushing down on here, can't get you a close-up, but if you were to imagine what it's sitting on, what this thread is sitting on, it's the female tooth. It's going to be sitting on the female tooth like this. The female tooth is here. And I'm applying a load down on the top, and so it's kind of pushing against it like that. Also, I'm going to be applying a torque. And the torque is kind of like, you can kind of imagine it when we've unwrapped everything as just a force. Okay, this here. So I'm going to call this force F, and I'll call this the force due to the torque. And we'll think about what that is in a second. Let's draw the rest of this free body diagram. And along this surface, we've got a pressure, and this relates to why we're using dm instead of either of these diameters. Along the width of this thing, so this thing actually has width out of the page because the tooth has some width as well. And so really we have this pressure over the area of these threads. And so that's why we want to represent it along a line instead. I told you we're going to unwrap a line around at a diameter dm that's halfway in between d and dr. Likewise, we're going to put a force in here that's just represented in the midpoint along the length of that line. And I'm going to call that n. And as we rotate this thing, it's kind of like we're pushing it that way, right? And so there's also going to be a friction force that's acting kind of opposing the motion, and that's just mu times n. Okay. So really we have a pressure on the undersurface of the thread. We have decided that when we unwrap this thing, we want to unwrap, just consider, instead of the entire surface, on unwrapping that, we're just going to unwrap a line. We're going to pretend it's actually just a line contact. And so we're taking the average of the outer and the minor diameter, the major and the minor diameter, the mean diameter. And we're also, when we unwrap it, we're just representing this pressure as just a normal force that's acting in the center of our little free body diagram here. That's what this n is. All right, let's think about that torque for a second. This torque force comes from the torque, right? And what force is just torque at a given distance. What's that distance here? Well, that distance, if I'm applying a torque about the axis, then the distance in question is 1/2 of the mean diameter. So it's this distance here. So this is really ft. We should keep in mind, I'll write this off to the side so we remember it later. ft is equal to the torque that I'm applying divided by the dm over 2. So maybe what I can say is that the torque is equal to ft dm over 2. So I'll just rearrange it like that. All right, so we have an understanding of the problem we're trying to solve. We're trying to figure out now what torque is required in order to produce a given force, say, despite the fact that we've got some friction acting on us. So how do we do this? We just need to sum forces on this thing here. Let's start by summing forces in the vertical direction. So the sum of the forces in the y direction. We've got a minus f, and then we have this n. Let's figure out what that is. If we had so remember this is our angle lambda here. If that angle lambda were 0, so if we had 0 pitch, if the screw wasn't a screw at all, but just a bunch of teeth that were rings, not a helix, then this angle would be 0, and we'd get n is exactly equal to f, right? It'd be kind of like we had drawn the diagram like this. It wasn't a triangle at all, really. It was just a block. Lambda is equal to 0. And so n would be pushing straight up. So n would be equal to f. So that tells us really quickly. I mean, we could think through it a little bit more carefully, but that indicates to me that we've got the component of n that acts upwards is plus n cosine of lambda, if we're trying to figure out whether it's a sine or a cosine. That's one easy way to think of it. You could be more careful and draw the angles appropriately. You could recognize that, okay, well, if I'm looking at the angle here, well, this has to be lambda, and you can prove that with some simple geometric arguments, and then you see it's n cosine lambda as well. All right, so n times cosine lambda, and then we're going to have a minus n mu n times sine of lambda. And that has to all equal 0. All right, let's go ahead and rearrange that. So we have, let's see, f is equal to n times, I'm bringing that onto the other side, but flipping everything around, we've got a cosine lambda minus mu n, minus mu sine lambda. Okay, and that is our equation there. All right, let's do some of the forces in the x direction. The sum of the forces in x is just ft. We've got minus n times sine of lambda that's coming from this guy, and then this one here is minus mu n times cosine lambda. That all has to equal 0 for equilibrium. And so we have ft is equal to n times sine lambda plus mu cosine lambda. Okay. Ultimately, what I'm after is ft, because if I know ft, then I can get this. So actually, why don't we rearrange that? We should go ahead and say ft. We should have solved for ft is equal to t 2t over dm. So let's substitute that in. 2t over dm is equal to n. Oh, let's solve for n. Okay, let's go ahead and solve for n up here. So n is equal to f divided by this thing, cosine lambda, minus mu sine lambda. That way we can go ahead and substitute in for n. We've got f and over a cosine lambda minus mu sine of lambda. And up top we have sine of lambda plus mu cosine of lambda. And so we have t is equal to f dm over 2 times this term. So f dm over 2, that sort of makes sense, right? It's a force times a radius. And then we've got some other terms involved. Cosine lambda over cosine lambda minus mu sine lambda. Now, in order to get this into the form that's written in the book, we're going to have to figure out what is the relationship between lambda and our lead and our mean diameter dm. We have that. L over pi dm right here. So another thing we've got the tangent. So we need to divide everything through by cosine, and that'll give us some tangents and so cancel other things out. So let's divide both the top and the bottom by cosine. So basically it's like multiplying by 1. I'm going to multiply by 1 over cosine lambda, and I'm also going to multiply by the bottom side by 1 over cosine lambda, right? So I haven't changed the equation. I'm just going to do that multiplication. F dm over 2. We've got a sine lambda. This actually becomes a tangent, right? Tangent of lambda plus mu times cosine over cosine, so that's plus mu, over, this becomes a 1 minus mu sine, it becomes a 1 minus mu tangent of lambda. So now we can go and plug this in so we can get it in the form that's written in the book. I'll do this on this line here. F dm over 2 L over pi dm plus mu over 1 minus mu L over pi dm. And so I think all I need to do now is just multiply the top and the bottom through by pi times dm. And that's going to give me that the torque that's required to raise the load is equal to F times dm over 2 times L plus mu pi dm divided by pi dm minus mu L.